Welcome to this recording for review 3 of MCS 320, a course on symbolic computation. So what I plan to do in this review is to present a summary of the first two parts of the course and also explain somehow how this course is going to end with a final exam on Friday, 5 August. So in the first two parts of this course, we looked at the essentials in symbolic computations. We compute with symbols, we approximate numbers, and build expressions. So the final exam will happen online. So you must, of course, use a computer, and all the questions must be formulated within a Jupyter notebook, one single Jupyter notebook that must be uploaded in time. I must be notified that you will be taking the exam, otherwise you will not receive the questions. Same protocol as the midterm exams, also the same format of the midterm exams. The main difference is that the scope of the material is the entire course. So this is review 3. We focus on the first two parts of the course, but the first review is also very relevant. So in total we will have four reviews for the final exams. We had two midterm exams, so the questions for the midterm exams are also very good problems. There were two versions, so even if you skip the exam, then please look at both versions. Even if you took the exam, look at the other version. Preferably look at the questions before you look at the answers. We had 5 quizzes. That was probably not enough, but the quizzes kind of point at the most essential problems, so there is focus there also. The homework problems, there were 7 homework collections in this course for a total at 28 problems. So also review the homework problems. Answers are posted. Make sure you understand your mistakes. It might not be all that bad to take your exam, to take your homework, to take your quizzes, and write your own corrected versions. So the most important resource that you build for this course are your own notebooks, and mainly that's then the expertise that you will have to solve the problems. Okay, so what have we seen in this course? So we started with the first part, which consisted of the first 10 lectures in the notes, our first 5 sessions. So the first bullet point is actually the most important point. By now you should be sufficiently familiar with SageMath, either that runs on your computer or in the cloud in Cocalc, and you should be able to use a Jupyter notebook sufficiently well. If you use code cells, please don't dump entire programs in there. Please try to separate it out. The interactive nature of a Jupyter notebook is extremely useful here. Even if you get stuck, use markdown cells to explain what you were doing and what the expected answer was to the question. So I will grade this and look whether you understood really what was going on. So in the first part of the course, we looked at number systems. So we can approximate with exact rational numbers or with floating point numbers. The symbol pi is for the transcendental constant pi. We have seen how to build rational approximations with a prescribed accuracy. we have been seeing how to use convergence, and then we also had approximations to control the accuracy. So there will be most likely 3 versions of the final exam. So for this question alone, I have 3 different types of questions. The other part of the first part was to look more at the data structures that we are using. So how can we store data in composite data structures, and how do expressions, how are they represented? So we have 2 types of representations for expressions. The fast callable objects, which then leads into running things fast by applying vectorization or cycle. So then the second part was on expressions. So that part was a bit shorter, only 5 lectures or 3 sessions. There we focused on polynomials, multivariate polynomials, polynomials in one variable, and general expressions. So note that fast callable objects are binary. Expression trees in general are not binary. So be very careful that you know the distinction between the questions. We have covered numeric factorization over the complex numbers, exact factorization, symbolic factorizations with algebraic numbers at root. So these algebraic numbers make the connections between the 2 parts. And there's also the link with the third part. So we have covered the interval arithmetic, which is a hybrid form between the purely approximate complex factorization and factorization where you still have bounds on the approximation error. In symbolic computation, we manipulate expressions, substitution, expansion, and again factorization. We want to avoid expressions. So rewriting expressions can be a very complicated and very expensive operation. We have, for example, seen the random point test to get out that problem. But in general, we compute normal forms. The normal forms actually then form the connection with the problem solving part in the fourth chapter of this course. So in this review, so this is already the third review, I hope you begin to start somewhere the connections, why the symbolic software is organized as it is. Alright, most important part, please review the reviews before you step into the final exam, or at least when you start beginning on the questions. Make sure that you have your material well organized. So speaking of organization, so here I'm pulling up a Jupyter notebook. So that Jupyter notebook is already formatted well. So what you will see are essentially the questions. And I hope that you will also use that format. You can start, of course, your Jupyter notebook in any way you want, but please also clearly indicate if you start typing up your own notebook which question it is that you are answering. It's good practice to start every answer with a reset. So you may not want to solve all the questions in linear order. If you get stuck, or perhaps you first look entirely at the questions and start at these problems where you know that you will have a good chance of success. Alright, so this is a review. I will try to showcase the most commonly occurring formats of the questions. So it's important that we can do things, that we can compute things, but it's also important that we can explain and that we can illustrate with an example. So sometimes I see then that people copy and paste everything that comes out of a Jupyter notebook for a lecture. Doing that is in some sense not really entirely wrong. It's good that you can see where we covered something in the course in our now 18, or this is the 19th session. But on the other hand, you will save time if you are really to the point. So what is the difference here between RDF and RR? Well, you can just ask Sage, but then actually in some senses this here, Sage that answers this for us. The double field is the real double field, which are the built-in hardware doubles. And then we have the MPFR, the wrapped real numbers. So here I let Sage answer this with the types. I did not use a markdown cell to summarize the answer, but the main, or perhaps I did. So here, this is the one-liner which explains the difference. There are the hardware doubles, which are typically faster, and then there are the the software doubles, which have a default precision of 53 bits. So RR is used whenever we want a real number approximation. RR has the flexibility, or with real field, we can extend the precision to any number of bits that we like. And that is then used in the second question. So the second question asked us to compute a sequence of 10 rational approximation with a prescribed accuracy. So the accuracy is prescribed to 2, 3, and 11 decimal places. There are two alternative versions of this question. I can ask you give rational approximations where the denominator is bounded by 2 decimal places, 3 decimal places, up to 11 decimal places. There you compute rational approximations which are larger and larger. Also more accurate, of course, but where you can bound the size of the numbers. The other alternative is to work with the continued fractions and the convergence of the continued fractions. So in that sense, the rational approximations kind of follow a natural progression. So that's another sequence of rational approximations. Okay, read the question first before answering to know what type of answer that you're going to apply. Alright, so the answer is in some sense very quick. So here we have the symbol, the square root of 3, which you can essentially interpret as an unevaluated function evaluation. And we ask numerical approximation with an increasing number of digits in the list comprehension, and we convert this to the rational numbers via the QQ. So very fast, very quick. Things to remember with Python is that the range stops at the last element minus 1. So you have to submit a 12 here. In the previous question we thought about bits. Here we actually think about decimal places. And I think there might actually be also a variation where you can set the precision in bits. A follow-up question here, verify the accuracy. So we have seen that you can do this. So I can ask you not for a whole sequence, but ask you to compute a rational approximation with 5 decimal places accuracy, and then to compute a relative error to verify that you have indeed 5 decimal places of accuracy. Okay, so these are approximations which are exact in some sense, an exact format. We can work with coefficients that are integers, but if we do modulo 31, which is a prime, then we can divide. So the rational numbers are very nice to work in. Every number has an inverse. You can actually also do this if you work modulo a prime number, because for a prime number is cannot be separated, so there is no way how you can write two numbers smaller than 31 so that their product equals 31. It's a prime number. And 31 modulo 31 is 0. So all the numbers from 0 to 30, so those 31 numbers, if you compute modulo 31, you cannot make 0. It's not like 2 times 2 modulo 4, that is 0. So 2 has no inverse modulo 4, and also not modulo 2 because it's 0. But here we have a multiplicative inverse, and we can compute with those numbers as they are the rational numbers. So how do you define this? Well, you can work with the Galois field of 31, and then here I indicated the multiplication table. So this is built in, and the multiplication table is, well, it's rather large, but it still can be read. And you can see how Sage does this, the symbols of 0 to 30. This is actually not the answer. I was just pointing out at the construction of the multiplication table, where you should see that AA is the absorbing element, the 0 element, and that the AA will not occur anywhere else. But the AB plays the role of 1, and on every row and every column, except the first column, you will see, in the first row, you will see one instance of the unit element AB. It takes a while to look at this, and this is not entirely the answer, certainly not. The answer is where you compute 1 over 7 and you cast this in the Z31, in the Galois field of 31 elements, or you do 1 divided by 7 modulo 31. That should work as well. Here I assigned this to I7, and even if you are, so 9 is the answer, and if you know 9 times 7 is 63, and modulo 31 you subtract 62, then you have 1. So you can essentially do the verification in your head, but here why not have SageMath compute this. You see that 7 times 9 in this modulo 31 arithmetic gives you 1, and indeed that satisfies this. An alternative question I can give you for any prime, or I can explicitly ask you to list the multiplication table. Alright, so let's then look for polynomials with coefficients in this finite field. Is this polynomial irreducible? Well, we can ask if it factors, and well, in some sense it does factor, but the 15 doesn't count. So this is a 5-degree polynomial that remains a 5-degree polynomial. Note that the factorization depends on the number field, depends on the coefficient field. So does a polynomial factor or not? If nothing is listed explicitly about the coefficient field, then we assume the rational numbers. There are other ways to solve this. So you can also explicitly declare a polynomial ring over the modulo 31 numbers. I explicitly verified the type, so we hammered on this throughout the course and especially in the first step. So everything has a type, and what you can do with the object depends on its type, depends on the methods that are defined. Here you can verify that this polynomial, so if we declare x as either a generator in this field, as this is called here, or in this polynomial ring, if we are using the symbol x, then it will be interpreted as a polynomial within that coefficient field. Okay. All right, so this is question 4. Question 4 deals with declaring variables. So we have seen the polar representation many times in this course. This is perhaps the first instance a complex number can be decomposed. And you have to show that you can make this decomposition starting from the left side. And the key to this is declaring the k as a real number. So it's a symbol. So here I now indicated this differently. We used a var, so that's another way of working. But here I'm explicitly using the symbolic ring and specifying that the domain is real. Then if I type this in, this is a complex number, I can ask for the real and the imaginary part, and that will give me the decomposition that I need. So in a way, this is verifying that SageMath knows this polar identity, this polar representation for complex numbers. All right. We're moving along. Question 5 is on the expression tree. So expression trees are not binary. What is here also a little bit special about this is that we have functions sitting in there. So you could think of binary operators, and this is now not binary, but it may also be unary. So the functions cosine and sine, they are represented as nodes in the expression tree which have only one child. And the child here for the sine function is the y. The child here, actually there are two children for the cosine, as we will see. Okay, how do we begin this? Well, we ask for the operands. So if we ask for the operands, then you see already that we have 3 children of the root, which is an addition operator. So the expression tree will consist of inner nodes, which are the operators, and the leaves are the operands. So if you are really in a hurry, you could make the first expression tree already here. But actually you should, hopefully you do have time, and you should use the operands and the operator further. So if you are experienced with this, you can indeed, but here look how necessary this is. You could think that the operand is minus the minus, that is an operand, that is a unary operator. So you can write minus, so 3 minus 2 is minus 1, but the minus is actually can also be interpreted as the one that you flip the sign of. You see that the minus z to the power 7 is actually represented as a product with two operands, the z to the power 7 and the minus 1. Here you see the cosine with the two arguments. The cosine actually has an argument, a list. Let's see how we're going to represent this. The power is something that we have seen. So at this point in time, we can write all the leaves, and the leaves are the variables, the symbols in the expression, and you can make your life a bit easier by choosing good names for the labels, for the name of the leaves. So Lx, Ly, Lz, and every constant is represented then in this way only once. So these are the leaves, and then you can start building up your tree from the bottom up. So the trees in computer science grow in the wrong way, so with the root all the way on top. What is new here is that you can interpret the cosine here. The operands of the cosine was actually the list, which showed up as the list, but you interpret this as another expression. So the expression is x to the power 3 minus 1, which is a sum of two operands. The x to the power 3, which is decomposed further, and then you have the minus 1. Okay, you justify this with the operands and the operator. And instead of the underscore add, you can write the plus, or you can write the symbol for the exponentiation. That is fine. Here you see the unary operator. The sign as a function works as an inner node, is placed as an inner node in this expression, and it has a leaf, which is the symbol y. Here is the entire expression tree then. Okay, so this is an important question, and not all questions will have the same weight. So questions where you only need to execute one command will have lesser points than questions like this. Okay, so we have seen the persistent objects. So this is an example here, and this is an example where it is the save and the load. So this could be formulated also as an explain question. Explain how in SageMath you work with a persistent object. So we've seen three examples of this. You can serialize everything, use the string representation, and then you have to use the pre-parse, remember? This way of working is actually the recommended way of working for SageMath objects, at least. And then we have the pickling, which is the Python solution. So for every Python object, you can pickle it before you then write it to file. Okay, here we are then at the fast expression evaluation. So here I give you how the expression should be really typed in. Looking at this expression, what would be the best way to evaluate this polynomial in one variable with very high exponents? So this is a general expression, and one way to do this would be to work with a fast callable. So with a fast callable object, you generate in essence, you define an algorithm as a data structure. So one can see this list as a list of instructions. And this can be used to automatically uh, count the number of operations. So you see how many exponentiations you need, so you can further look at the um, cost, the arithmetic cost that needs to be done. So the total number of operations is 30, but that also lists the data transfers. In the purely arithmetical operations, we have 6 exponentiations, 6 multiplications, and 5 additions. So that means that if the power is actually quite fast, then especially for high powers, then this is a very good way of working. Um, if you would do it in a straightforward way, so you evaluate monomial per monomial, then you would need 948 operations. Now note, this is what we call a sparse polynomial. It's a polynomial of a very high degree. The degree is 298, but only very few terms appear with non-zero coefficients. If you have a dense polynomial of 298 and you do have 299 coefficients, then you are recommended, if you then want to do this in the fast possible way, then you must use the Horner form. So I'm telling you now an alternative, another version of the same question, where you are given now a polynomial where every power, every possible power up to the degree of the monomial appears with a non-zero coefficient. Okay, so then going more into the efficiency, let us consider vectorization. And this is a review question, which gives you kind of the whole context. So what I could do on the final exam, because I'm asking for vectorization, is already give you the Python function. But again, so as part of this course, you should be able to translate any expression written in mathematical form into a Python function. So this comes then more into the other parts of the course, which is the second, which will be the fourth review, if you remember also the second midterm exam. Okay, Python is often blamed to be slow. In scientific and numerical computing, we have NumPy, and with vectorization, we work with functions which takes on arguments entire vectors. So instead of doing this in the list comprehension one by one, which is interpreted and in a way often also quite accurate, because you're going to run these list comprehensions with exact arithmetic. So if everything is written as here, you do this with a rational approximation, and all the arithmetic happens with rational numbers. With NumPy, we are immediately also working with floating point numbers. Now I'm spending some time on this question because it's important that you parse everything what is required. So when you have to write a function, you have to be aware of what are the input parameters. Here there's only one input parameter, n. N is the dimension. So there are many symbols here. So there is the k, that is a symbol. The k is a secondary loop variable. So Python is very efficient, very short, so you can essentially translate the sum function in a lambda expression. So here you see going, oops, I should have scrolled this a little bit better. It's kind of unfortunate that the sum comes out of view if I have the lambda expression. Let me simply try to wiggle it a little bit. I don't think it's possible. But the point, oh no, it is possible. So here you see on top of this question, we have the typeset formula, and at the execution cell 43, you see the lambda expression. Now again, I'm giving you the solution. So if you build this up, some people get confused with all the brackets. So all the round brackets, you may have to do this in multiple stages. Okay, then verify the correctness. So it's important to be fast, but it's most important to be accurate. So something that I had to squeeze in. So in a way, this is a review for the final exam. So notice if you have to do numerical integration, you use the hold equals true to prevent the evaluation, because I'm only interested in the numerical value, which by the way here coincides with the numerical approximation to 10 decimal places. So this integration rule, and that's also somehow an advertisement for the SQL course, this rule which I have given you here is actually quite a good rule for estimating integrals. 10 decimal places. And this was done in milliseconds. Pretty fast, but we can actually do a lot better. We can go a magnitude faster, go to microseconds with vectorization. So what's the deal? You could say milliseconds is already fast enough, but if you have to run this many times, it could really pay off. So here is the solution. Perhaps pedagogically not that good, but you see the entire overview. We import NumPy, and then we define the Python function. Why we have to define this in a Python function? Because we want to time it. Now again, if you do this, and even if I prepared this question, for the sake of presenting you with a wide range of questions, I give you the final answer. But when I solved this, I also had to break this up in pieces before I was sure that everything was correct. But you see the point. We are using linspace to define the vectors which are here now called PTS. So these are the points. The points start from k equals 1 to k equals n minus 1 in the formula. And so we have n minus 1 points in the linspace, and the increment, it doesn't really start at 1 because we have the 1 here sitting in the outside and the 2 sitting at the other side that we add in the beginning terms of this numerical approximation. But you see that this is the vector to which we apply the inverse and then the sum. So there are 3 operations that are defined within NumPy. And that is done with optimized arrays. So we work with floating point numbers and with optimized index arithmetic. And you see that we go from milliseconds to microseconds. Okay. So I'm 40 minutes into this lecture. I have 10 minutes left, which is too little to simply browse through the remaining questions. I will be quick here for this expression tree. In some sense, this is an extra question, a little bit easier than the expression tree that we considered. Then we have the exact factorization. where here I'm actually asking for the square root representation. In school, we all memorized the quadratic formula. Well, there's also something like the cubic formula for the roots. And you could declare that to be the exact factorization. So here you see the roots. It's actually not pleasant to look at. So the numerical, but it is over the complex numbers. So you see the capital I, and if we just make the product of these factors x, you then actually see the factorization coming up. And again, it's not really good to look at. But this gives you also a little bit of an expression how this factorization is actually the same thing as x to the power 3 minus x minus 2. So this is another example of expressions, well, by forcing an exact computation. Okay, so we have three more factorizations. The numerical factorization, which works over the complex number field, and this can always be done in one statement, essentially. You convert the polynomial into the CC field. So we started this review with the question, what is the difference between RDF and RR? There is also the CDF and the CC. So there is a very analog question here. So CC is good to know, complex double precision over the hardware, 64-bit floats. The symbolic factorization starts with verifying that your polynomial doesn't factor over the rational numbers. We've done this already with the cubic formula. So here is another. So here I'm using this number field. So we are using the number field where we are using the polynomial as the extension. So alternatively, we have worked with the polynomial ring and then with the dot extension where you give the polynomial. Here I give another syntax, not to confuse you, just to give you another way of working. Where here actually we work purely formally. So the result, you see what we obtain is perhaps not so useful because it's x minus a, x minus b, and then the conjugated root, the a plus b, or the minus a minus b. So this is the purely symbolic factorization, where we have declared the a and the b as roots of polynomials. Note that we have to factor and select the irreducible factor. You may not extend with a formal root for a polynomial that does factor. Sage will complain about this. You will get some very nasty wording. And lastly, there is the symbolic numeric factorization, where we work over the complex interval field. You see the question marks. So all decimal places before the question mark are, which we can assume are correct. All right then. I have a couple of more questions to show. Here we have the partial expansion, so you want to expand the second factor but not the first one. How can you do this? You can do this by shielding the first factor from expanding by substitution. So we introduce a new letter, and actually the z is already immediately introduced here in the solution. It would be pedagogically better to only introduce this in the cell 63 here. So we're going to replace the expression x plus y by z. So that is the dictionary argument in the substitution. which has the advantage that we can provide an expression as a key. We can also do the symbolic evaluation, where if what we substitute is just a symbol, this actually goes quicker than working with the dictionary. Alright, question 12 is on another form, the partial fraction decomposition. So here I give you a rational form typed in, and then compare this to the evaluation of the Horner form. So you could use the Horner form for numerator and denominator. What if you would use the partial fraction decomposition? The partial fraction decomposition is defined over any number field, but here it works best over the complex numbers, where we see that everything factors fine, so we are actually trading in multiplications by divisions. So here I have used the property that a Horner form of a degree 5 polynomial needs 5 multiplications and 5 additions. If you would do this, you would end up, so the numerator and the denominator are both degree 5, so you would end up with 10 multiplications, 10 additions, and 1 division. Here with the partial fraction decomposition, which is actually also using a root finder, you actually end up with 5 additions and only 5 divisions. So this is a lot better. Last question is explaining. So why are normal forms important? We often end up with expressions that are often representing the same mathematical object. And of course we want to simplify, we want the simplest form of the expression. So the deciding on whether a normal form, whether two expressions are the same, is actually also very similar to deciding whether an expression reduces to zero. Now, we've seen many normal forms. For example, if you normalize a rational expression, this would mean simplifying, which is not only always simplifying, by dividing, removing the common factors in the numerator and the denominator. And that's actually what the question is asking about. When is a normal form too expensive? And then is when you have expressions well. In the answer, I would like to see the term expressions well. And here is the example. You see, if you ask for the numerator, where by default you actually normalize, then you end up with a long expression. To avoid this and still decide whether this expression is now 0 or not, then you can evaluate at a random element. And this shows here in this case, here we see the RR again, which is very useful. We started this review with that this expression is then not 0. Alright, I hope this review was interesting. As you can see in the total number of statements, I have too many to be healthy for one session, but I hope at the same time that I have given you a good overview of what the first part of this course was about. Thank you for watching. I hope this was interesting.